So it's super amazing because I did this entire video and then I found out that the noise was all messed up. So I'm going to be re-recording the audio, but hopefully we'll be able to keep up with what's going on the screen. So basically what we're going to do here is look at recursions with the Repertoire method. So a recursion would be something like this, where you have t sub n, 2n squared, plus 7, plus tn minus 1, with some kind of a base case like t sub not equals n. And what you're trying to do is you're trying to get a closed form for this. Does that make sense? So you're trying to think about it, you can't figure it out, you kind of stare at it, it doesn't make any sense, you try to look it up, nobody has this because this is a super special recursion that you're the only one who's ever thought of, so you've actually got to figure out a way to put this through on your own. All right, so what we're going to talk about is building a repertoire. And so like, I don't cook, I eat Hot Pockets, but from what I hear from people who cook, you like go to your cabinet and you're like, I know how to boil eggs and cabbage and ham, and then I go look at my fridge and I see cabbage and ham and peas, and I'm like, oh, I could take that and that and that, and I could put it in some kind of a pot and make a lasagna or something. Obviously, yeah, cooking is weird, but basically we're going to do the same thing but with math, so it's like way better, because why would you want to cook when you could do math? So what we're going to do is kind of build a mathematical repertoire that we can use to eventually go through and put something in with this and turn this recursion from this kind of recursive form into a, what we would call a closed form. So basically our goal, so like if you're talking about a recursive, we say, well, this is in terms of the previous term and this is in terms of the previous term. So if I want to know the fifth term, I have to calculate the fourth term, and to get the fourth, I have to do the third, and to do the third, I have to do the second, and the second, the first, until you get to the base case, which is 0. So that's kind of annoying, because what if I want the 8 billionth term? So you'd much rather have something that's just like a function, where if I give you 100 billion, you can say the value of 100 billion is blah, 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 blah. And you're like, great, okay, so that's where we're trying to go with it. So actually what we're going to end up doing is, instead of trying to take a recursive and guess the closed, we're going to start with the closed and then figure out what kind of a recursive definition goes along with it. So we're just going to kind of practice with that. And this is going to be super contrived because I know where we're going with this. You'd be like, why are you going to choose this letter? And I'm just doing it because I know where we're going and I value for that and stuff. But we basically are going to start with some b sub n is equal to n squared. So that's a closed form, because if you give me 8 million, I can say that b sub n is 8 million squared. Or if you give me n equals 3, I can say b sub 3 is 9. So I don't know what the recursive version of this is, but there's got to be one, right? Because, I mean, math can do everything, and I got nothing else to do tonight, so let's just work on this. All right. Now, anytime I'm doing a recursion, I can always start with coming up with a base case. In this case, it's super easy because it's b sub 0, 0 squared, which is just 0. So that's kind of the base case for my recursion. And I know that a recursion is going to look something like b sub n is equal to blah plus b sub n minus 1, because that's what recursion looks like. So it's super easy. I just have to come up with blah, and then I'm done. And I don't know why this stupid video is so flippin' long, because all I'm doing is coming up with this stupid blah thing. But it's cool. So I'm going to replace the blah with a little b sub n, and then I'm going to try to figure out algebraically what that little b sub n is. So I have b sub n, I know for sure, is n squared, and because I defined it that way. And I also know that b sub n minus 1 is going to be equal to, n minus 1 squared, because again, kind of awesome at, math. By math, I mean algebra. All right, so basically what I'm going to do now is I'm going to plug those values in. Let me move this over so it kind of lines up a little bit better there. So I've got n squared is equal to I don't know what it is, but I'm going to call it little b sub n, plus the big B, n minus 1 term, which is n minus 1 squared. And because, again, super awesome at algebra, I can factor out that little polynomial thingy, and I can see that the n squareds cancel out. So I end up with little b sub n is going to be equal to 2n minus 1. So now if I plug that back into my original recursion, now all of a sudden I have this recursive definition of n squared, which is actually kind of cool. So I can tell you that b sub n is going to be equal to 2n minus 1 plus the previous term, and the first term is going to be given as 0. Okay, so that is going to be the exact same thing as that closed form, which was b sub n is equal to n squared. All right, so again, what you see on the left is considered the closed form, and then what you're going to see on the right is considered the, gosh, I can't, writing is hard, is the recursive form. So what's nice about this is I'm actually like buying, back to our cooking analogy, I really like a better analogy than that. But your cooking analogy is like, officially I've bought something for my little, I've never cooked before, so I'm gonna put something in my pantry, and I have this beautiful closed form to recursive form in my pantry, and I'm super excited. I'm gonna invite all my friends over to come see it, because that's what you do when you come up with a closed version of a recursive version of a closed form function. Woohoo! So now I could go do this and show you it's true with proof by induction, but quite frankly, I've lost too many friends that way. So we're not going to do it with proof by induction. We're just going to do it by, like algebra and stuff. Make a little table, because charts are cool. So in the closed form, I've got n, 0, 1, 2, 3, 4, whatever makes you happy. You can do this as much as you want, because obviously you've got nothing else going on. So for each of those squared terms, I've got 1, 4, 6, or 1, 4, 9, and 16, because I can square terms. So let's look at the recursive, and it's going to be a little different to put together. No, not that. And then we'll put together the chart. So we'll start out with n is equal to 0, b sub n 0 is 0, because that's defined. Then whenever we look at n equals 1, then we know it's 2 times 1 minus 1 plus the previous number, which gives us 2 minus 1 is 1. Woot! All right, for n equals 2, 2 times 2 minus 1 plus the previous number. Again, those 2's, make sure you know which ones are being subbed in. So 2 times 2, and then minus 1 plus the previous number, which is 1, and that gives me 4. Then for n equals 3, 2 times 3 minus 1 plus 4, because that's the previous number, and that's going to give me 9. And then when I plug in the 4, 2 times 4 minus 1 plus the 9 previously, and that's going to give me the 16. So, I mean, we could do this forever, and I could really prove it for realsies, but I think this is a better way to demonstrate that, first of all, how recursion works, and also to show you that what we have is actually kind of super legit and kind of awesome. So we now officially are really confident in this, and we can go try to remember what we were doing in the first place, which was to try to find that stupid 2n squared plus 7 thing that you see at the top. Now the problem with what you might see here is we actually have a 2n, but what we're looking for is a 2n squared. So when we guessed an n squared, and we ended up with a recursion that was in terms of, down here, n. So since we guessed an n squared and we ended up with an n, then we're like, well, maybe if we guessed an n cubed, we could end up with an n squared. So that's pretty much where we're going to go from here. So, all right. So let's guess our a sub n, and obviously I'm working backwards, so I'm going back to a. So I'm going to guess a sub n is equal to n cubed. And that means that if I'm trying to find a recursion that goes along with it, it's going to be needing to look more like what we had before. So we're going to start out with something like a sub naught, or a sub 0 is 0, that's our base case. And that a sub n is going to be equal to some little a sub n plus the previous term a sub n minus 1. And now we're going to go try to figure out what do we need to do to make this recursion work. We got n cubed is equal to a sub n plus n minus 1 quantity cubed. All right, so I can do and do, and because I'm kind of awesome, I know what this is going to look like. And if you're like, how are you that awesome? Just remember it's Pascal's triangle. So if you do your little 1, 1, 1, 2, 1, 1, 3, 3, 1, those are those coefficients there whenever you do that expansion of that little thingy. So again, the n cubes cancel out, and I end up with a sub n is going to be equal to 3n squared minus 3n plus 1. Woohoo! Which means now I have an amazing closed form that is connected to a recursive definition, which is what I have above. So the big a sub n, 3n squared minus 3n plus 1 plus a sub n minus 1, and then of course the base case, you can't see what I'm doing, a naught is going to be equal to 0. All right, now we're cooking with gas. That's what cool people say, right? We're cooking with gas. Oh, it matches our little theory that this is like cooking, except I don't know, is cooking with gas like a thing? All right, so basically now what we have is we have that n squared term, which is good because that's what we were looking for. Or we have this n cubed and we have this n squared, and we're thinking maybe there's a way that we can use these together to eventually accomplish what we're looking for. So remember that our goal was to actually come up with a closed form of this recursion that we had before. T sub n is equal to 2n squared plus 7 plus t sub n minus 1. Now we have that n squared term in the thing that we just came up with. Now it's not exactly perfect because we'd have to scale it by like 2/3, divide by 3, multiply by 2. And then unfortunately that introduces that 3n term, which we can actually use the b series to get rid of. So okay, we're making progress. We can use that b thing somehow, maybe, to get rid of that term. Now it's just left to getting rid of that constant. So we're going to come up with one more recursion closed form combo, and it's going to look kind of stupid because you're going to be like, I already know this. I could figure this out on my own, but we're just going to go through the process anyway because it's kind of gratifying to see that you do something really complicated and get a really simple answer that makes sense, which kind of gives you a little bit more faith in the process. So again, we're going to start off with c sub n, and we're going to make this equal to just the standard layer n. So we're going to then put together our recursive definition. So we've got our base case. So it's going to be c sub 0 is equal to 0, and then c sub n is equal to some little c sub n plus c sub n minus 1. This is all making sense now, right? You're like, yeah, absolutely. I'm totally not just having this on in the background while I'm, I don't know, trying to fall asleep or something. All right, so I've got that c sub n is equal to 1. So I've got that c sub n is equal to n is going to give me the same thing as the recursive definition of c sub n is equal to 1 plus c sub n minus 1 with a base case of c equals 0. And this is where you should take a moment and realize that we just proved recursion with counting, because remember c sub n is equal to n is like counting, right? So if I give you, 0 or 1 or whatever, then it's 0, and 1 is 1, and 2 is 2, so you're basically counting. So this would be like if you're trying to explain counting to someone who's really having a hard time with the concept, you can just be like, okay, so you're going to start with a base case of 0, and then each time you go through, you're going to take the previous value that you were on and add 1 to it. Got it? So if I have on term 1, the previous term was 0, so 1 plus 0 is going to be 1. All right, so when I'm on 2, then it's going to be 1 plus the previous term, which is 1, and then I'm going to be at 2. So it's kind of stupid. We just proved that counting is a recursive process, but that's okay because there was a reason that we went through all of this crazy. So with the magic of copy, paste, etc., this is what we have right now. We have our goal, and we have all the stuff on the right that we came up with, and this is actually called our repertoire. All right, so this is our official repertoire, hence the repertoire method, and this is what we're going to work with and see if we can come up with how can we manipulate all these to get what we have on the left. Make sense? Good. All right, so basically what I'm going to do is I'm going to guess. I'm going to say, I think there's a way that I can scale a sub n, and then I can scale b sub n, and then I can scale c sub n. So I'm going to call all these scales alpha, beta, and gamma. So I have alpha, a sub n, beta, b sub n, and gamma, c sub n. So similarly, I could also write this as terms of n minus 1. So I have alpha n minus 1, beta b minus 1, and gamma c n minus 1. All right. And I'm going to see if I can get all this to make sense and figure out if I can get valid values for alpha, beta, and gamma that I can actually use to make this all work. Get. So now it's coming down to just kind of plugging in what we know. So I have alpha, a sub n, and I know from what I have above that a sub n is going to be given by 3n squared minus 3n plus 1 plus a sub n minus 1. Now I'm going to go ahead and put in the beta. And so with the beta, I'm just going to, again, use that recursive definition, because remember that was the whole point of what I'm trying to do, is I'm going to try to take that, match the recursion, and then use that to go back to the closed forms that I know. So I'm going to plug in the b sub n term. It's going to be 2n minus 1 plus b sub n minus 1. And then I'm going to throw in the gamma, 1 plus c sub n minus 1. Then I'm going to do algebra, and I'm going to combine all the terms that I need to get them where they need to go. Make sure you can see what I'm doing. All right. And ta-da, algebra. All right, so what you'll see here is I've actually just reorganized the terms, and I've grouped them by the order of n that they are. So this is the n squared term. I have the n to first term, and I have the, I'm going to switch colors here. I don't know why, because I like colors. And then I have the n to the 0 term, or the 1 term, the constant term. Okay, now something else that you might notice is what I have right here. Now this should look super familiar because we just wrote it like a minute and a half ago, and that is going to be equal to what you see right here. So that's actually the tn minus 1 term. So I'm going to go ahead, I'm going to rewrite all this, and I'm just going to put the tn minus 1 term there, and then you'll be able to see how they're connected. All right, so that's what we had, and now we need to go back and we need to think about what our goal was. what we were trying to do is to come up with some closed version of this. So we had 2n squared plus nothing n plus 7 plus t sub n minus 1. All right. Okay. So now basically it's just a game of match and pattern matching, and it's super amazing. So I'm just going to compute or take anything that's associated with the n squared and set those equal to each other, anything with the n and set those equal to each other, and the constant term and set those equal to each other. I'm just trying to figure out what those alpha, beta, and gamma values should be. So alpha is 2/3, which we kind of suspected. We had that up before. So negative 3 alpha plus 2 beta has got to be equal to 0. And so I've got, wait, not that. I'm going to go 2 beta. So 3 times 2/3, and because I'm super good at math, I know that means that beta is going to be equal to 1. This is always the stuff I mess up. Okay, so then I've got alpha minus beta plus gamma has got to be equal to 7, so I've got 2/3 minus 3/3 plus gamma is equal to 21/3, giving me that gamma is equal to 22/3. All right, so now I've got alpha, beta, and gamma that are matching what I was trying to find a match to, and you're like, I'm still not 100% sure what we're doing. You're probably going to feel like that even when the video's over, but look what we have is we now have something that in a minute you're going to see we can now get the closed form for our recursion that we're trying to figure out. Okay, here's the big potato. Big potato, is that a thing? So I have 2/3 a sub n plus b sub n plus 22/3 c sub n. All right, now I actually have closed values or closed forms for an, bn, and cn. So what I want to do next is I want to actually take those values and plug them in. Okay, so I have t sub n is going to be equal to 2/3, and a sub n was equal to n cubed. N cubed, n squared, and n. Those are those, so those will be easy to remember. So 2/3 n cubed plus n squared plus 22/3 n. And that is actually the closed form of what we're looking for, of our repertoire. Now, as I'm writing this up, you might be like, wait a second though, there was that base case, and I'm pretty sure that if I plug in a 0 there, I'm not going to get a 7. And you would be absolutely right. So this base case being 7 thing actually opens up all kinds of crazy, and in the interest of keeping this video less than 5 hours long, which we're getting kind of close to at this point, I'm going to ask you to kind of leap of faith this thing and just kind of trust that we're cool. So we're actually in this really unique position that we can fix this very easily by you can just say, well, I'm just going to add 7 to it and it's going to work. And indeed, it will. And that's because the way that this particular recursion is set up, that 7, once it starts, because it initializes our recursion, we put that 7 in there to begin with, and then every time we're only adding the previous term. We're not adding double the previous term or triple the previous term. So the fact that we have a 7, it's just going to be 7 once. It's not going to like propagate over and over again. It's not like every time we follow through the recursion, we're going to get that 7 in, double it, and then double it, and then double it, or triple it, and triple it, and triple it. Every time we go through, that 7 is only going to happen once. But just kind of to remind you that this is a thing, I'm going to put this 1 to the n there, just so you can kind of be like, oh, I remember that was there for a reason. And then eventually, whenever you see a recursion where it's like blah, blah, blah plus 2 times t to the n minus 1, if it's 2 times t to the n minus 1 or 3 times t to the n minus 1, then you would have 2 to the n or 3 to the n in that correction term for that base case. So again, just so we're super clear, what I'm saying is that what you have here is the closed form and the recursive form, and they're both equal to the exact same thing. Now, again, this is something that I could prove using proof by induction, but a lot of times if you're not super comfortable, you do this whole proof by induction thing and you're like, I don't even feel like I did anything. So what I'm going to do for you is basically the next best thing is I'm going to put it in Excel, because then we can just like drag the columns down, and then you're maybe a little bit more convinced, because even though proof by induction is the correct and the big manly way to do recursion, we prove by induction here, son. We're instead of doing that, we're just gonna like put it in Excel and be like, okay, I believe it, because I just want to know that this works. And again, I can get super crazy and prove it by induction, and it's not super hard, but let's go ahead and we'll put it together the recursive way here. So it's no, not 7. It's gonna be 7. So I've got, it's gonna be 2 times the n. Plus 7 plus the previous term, which is 7. And so if I drag that down, those are going to be the recursive numbers that we come up with. And I can do the same thing for the closed form. And I copy that just to get the table, but not those values. All right, so for the closed form, that I created myself, it's going to be, not that, it's going to be 2/3 n cubed. So that thing cubed plus n squared plus, and I realize you can't see what I'm typing, that's okay. Oh, yeah, there we go. Plus n squared plus 22/3, and wait, that's not an n, there's not an actual n, I gotta refer to the stupid cell. N squared, there we go, plus n plus 7, and so that's just the closed form, so it doesn't refer to anything but the n itself. And in fact, now if you look at those values, you see that they are fundamentally and phenomenally and amazingly the exact same numbers. So just to make sure you believe me, let's go ahead and do a little calculation where we have the difference between those two values, and we're going to take that and drag it down. And because this is Excel and we have nothing else to do, we're just going to drag it down and 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 down. And look, they're all the same. And you're like, but it says blah blah blah. But no, it's like seriously the same. Like no matter how far down we go, it's going to come out to be the exact same values. And so again, you can prove by induction. This is, I mean, if you're just trying to demonstrate it, this is a pretty good demonstration that at least for the first, 1912 terms, that this is a valid thing. So this is a really, really cool thing. There's a whole lot more you can do with this, but hopefully this will give you like a nice initial flavor to get you excited and out there to attack some more recursion to closed form problems.